Resume.
Okay, yeah.
Resume.
All right. Ladies and gentlemen, it's your turn.
Hello, everybody. Sonia, that will be running down the experiment, and myself will give you a small tour to CMS for the
Andrew
ones.
Makitsiro and Sonia
Sonia
Natale.
Natale.
Yes. And now maybe we can introduce ourselves. Okay.
Yes.
Do you want to start, Andromaki? And then I will.
Okay, so I'm Andrew Makitsiro. I am at CERN working for the CMS detector. Before I worked for another detector that most of you do not even remember now. It's Delphi. It's where another CMS detector, another LHC experiment is taking place now. So I'm here, I'm CMS from the beginning. I started working with the tracker, and I keep working with the controls of all what we call cold systems. I am Greek, and I could call myself a real and applied physicist more than anything else. But you know that in this job, you've got to do incredible things, and we'll find out about them as we go.
Let's just not forget about Marzena Lapka, who is remotely connected, and she is going to handle the questions for today. Hi, Marzena.
Hi, Marzena. And I'm Sonia Natale, coming from Italy. I did my master in Rome, even if working on an experiment at CERN, which maybe nobody remember, L3.
Oh,
I do.
Sultan, he remember? Yes, that was the last time. Let me say, it was the last time of my master thesis. And then, okay, I moved to, I did my PhD at University of Geneva, working on an experiment which is currently installed on the space station, which is called AMS, Alpha Magnetic Spectrometer. And since a long time, I was working in this experiment, both in the construction, the commissioning, and then the data analysis. But in parallel, I always thought it's important to also drive the message of this scientific communication message to everybody. Now we know we have alumni, maybe technical people, and also non-technical maybe. So, and this is why I enjoy also to do this kind of activity. And today we are in the control room of CMS, this experiment, and Andromaki, she said very well, on the accelerator LHC. We are at the point P5. And I will go underground to show you through my eyes, through my hands, because I'm also an applied physicist.
And an Italian, so she will use her hands.
Yes, of course. So even if there will be no communication, I can still
exactly.
I can still talk with my hands. And so I will try to make this visit as alive as possible. Even if we are remotely connected, I hope you will enjoy this visit.
Okay.
I prepare myself,
yes,
maybe?
Please.
Okay, I go, so you will see me, I prepare myself. I need to do some steps. You will see me preparing, and then I will start to bring you with me. Okay, see you in a while.
Oh. Yeah, I think we can.
Yeah, we can start. We can keep you company while our two colleagues are getting prepared to descend to more than 100 meters underground in 3 floors actually, and show you around with an old detector that got the latest revamp for the new data that is going to start arriving in the new year. Ourselves, I mean, you are alumni, but we have no idea what alumni you are. You might be friends and families of alumni, so we will give a short description of what CMS is doing. CMS is one of the 2 general purpose detectors that are on LHC, and LHC is the largest machine ever built and has as role to accelerate protons on a large ring that's almost 27 kilometers going from the Jura Mountains to reaching Geneva, the airport of Geneva. LHC is actually taking it's following another CERN accelerator that was called LEP. It's where we all started. So the tunnel pre-existed in more or less the same form, but then it got refurbished with extremely elaborate magnets in order to assist the acceleration of the protons, to assist having protons inside the ring. So LHC is the biggest accelerator we have, and it is a proton machine. Then it houses 4 detectors on it. You can think of the accelerator always as this huge underground donut that is between 60 and 120 meters in the depth of the French-Swiss border. The tunnel itself is about 3 meters high, so it's this donut, the 3 meters high. But where you have the experimental areas, the detectors, of course, you have a huge bubble in your donut. And in every one of those, you have one giant camera, which is what a detector is. And when you see exactly what this is, what Zoltan is showing you, the amazing and beautiful magnets that made LHC a possibility. And that is the real breakthrough, almost 2,000 of dipole magnets and lots of other magnets along the beamline. And the 4 big experiments, out of which Atlas and CMS are what we call general purpose.
Andromache, sorry to interrupt you.
Absolutely.
Yes, okay. Do you want me to show how we enter here in the experimental? Because I'm already behind the control room, and I have to go through the door, which allows me to go to access the experimental area. Do you want me to show this?
I think that the people want to see this.
Exactly.
And
yes,
see
okay.
you fighting against the door.
Well,
yes, exactly. So now, okay, let's do like this. Okay, let's start. Let's make a connection with movies and Hollywood movies. If somebody has seen the Angel and Demons movie, you can remember maybe that there is a cruel scene inside through these doors. Fortunately, this will not happen to me, but I had to do 3 checks. One is a weight check to check that I'm human, let's say. Another check is through to check that I'm not bringing any object with me, and is done with infrared beams. And the third one is the iris check, both eyes, so the biometric check. Let's say this is the door to enter the experimental area only for people. I will show you where the one for material. So I go, I have this dosimeter. This allows me to enter. We can show how it works. So I badge here and I enter. Bye.
Well, in the meantime,
we can, while they are struggling to get down, they're not struggling actually. They
are very well experienced.
To know perfectly.
Yes, of course, we hear you.
Can you hear me? Yes,
yes,
okay.
Definitely.
Okay, you cannot see me because now Noemi, we didn't talk about her. She's helping me with the camera today, and so she had to badge too. And when we enter this door, okay, I'm still here, yeah. When we enter this door, I'm jumping up and down the screen. So when we enter this door, as there are these infrared beams, we cannot bring the camera on the top, so we had to hide it. This is why you didn't see anything. Now we are in front of the elevator. You see, it's at -3. We have 3 levels underground. The -3 is the lowest one. Then we have the -2 and the -1. -3, let's say, is basically -100 meters, -2, almost -90 meters underground, and then you have -1, which is -80. I will call the elevator, and the meanwhile, you see, we can see it's moving, you see, but maybe I can ask Noemi to show in the meanwhile the blue door. You see this blue door? Okay, in case you would have come here, as you in the database, you do not have your, let's say, information, biometrical information there, you cannot use the door we used, Noemi and I, we used. So you had to enter through the material door, unfortunately. But however, we are always happy to welcome people here, so it's just to make it faster. And then I think our elevator is almost here, -13 meters, and you will see is a big elevator. In normal time, we can fit inside even 40 people, but you will see on the floor, now we cannot. We have only few positions here, and maybe Noemi can come. Okay, and so I push the button, we will go to -2 or -3. Okay, we go immediately underground. So you will see the basis of the detector, and consider that these, I don't know if we lose the connection. Let's see. In case we...
Yes, we lost the connection now.
You lost the connection?
This is a normal thing in the elevator. This we expected, indeed. On the way down, it happens always. On the way up, it usually doesn't happen. This is the secret of how the roaming is happening from France to Switzerland. And
I'm here.
There she is.
Can you hear me?
Yes.
Okay, still here. You will never, you will see me every time today. So I was saying that, okay, now we are going in a place that usually for visitors is not allowed to go. So I would say it's not just an advertisement. Consider it's a virtual visit, but you gain something even if you are not here, and you gain that we can show you places that usually normal visitors cannot see unless they are working at CMS. And sometimes, okay, even if they are working in CMS, they are not going everywhere. So you should be allowed. Now, this is a special visit. You see, I have another door now to batch again. Same procedure. So I will not explain, you just see me, and then, okay, we will wait for Noemi. Let's go again. This is yellow, this door is another access, but however, the system is the same. I enter, I check my weight. I check
Actually,
yes?
This is a different color. Do you know?
Yes. No, I leave you to say, because they're different.
Oh, yeah, okay. So we have different colors on the doors, green, yellow, and red. It's not just because we didn't have enough paint. Everything has a meaning. The green door means that even if you break through the door, nothing serious will happen to the accelerator. Red and yellow are interlocked doors. The red is always interlocked. If you break through it, then we lose the so-called patrol, even if there is no beam. And if there is beam, in addition, we shut down the full accelerator. Yellow door instead doesn't lose the patrol probably, but this also shuts down the accelerator if there is beam in the machine.
Nobody can take the risk.
Yeah. All doors are equipped with camera from both ends. So if you do so just for fun, you must have a good explanation. All right.
Okay, so we will be very careful to enter these doors. However, you see, okay, I enter this corridor. You see, there are some corridors. We should say that this is not just for fun. This is also a rule that you can find not only here, but in all the places where there is a background of radiation. For example, even in factories, and nuclear factories, because particles, they go straight forward. And so in case there should be, but here is not the case, but there should be any incident, I would say, not an accident, you can always, how to say, repair yourself behind the corner. I'm trying to play the game with the Noemi. Now, here is the door. We enter the experimental cavern. We will see, and you will see, CMS.
It's hold your breath.
Yeah, this is a very heavy door.
Yeah,
this
heavy
holds
door.
The pressure difference.
Yes, exactly. So, okay, I think the best thing to show, we already see now, if there are, let's say, purists of physicists, let us say, I'm a physicist, as Andromachy, I built detectors, but I like always to show even also to normal people that, okay, we can compare and we can enjoy physics, not only because if you're a technical person, it's nice, but also because you can compare. So I don't know, imagine you have a salami, I'm Italian, okay, so you have a salami, a long salami, and now you see only the last part of the salami, okay, the cross section, and I will go there to show you how big is this object. Consider I'm more or less 1.60 m, I'm not very tall, but however, you will see what it gives. Come with me. Can you see? And this is only the feet of the experiment. Look, this is a building of 5 floors, okay? The diameter of this object is 15 meters, okay? And now, this is the cross section. The length of this salami, or let's say, in a more, let's say, serious language, the length of this cylinder, this experiment, is about 24, 25 meters, depending what you consider it together. And so 24 means a building of 8 floors. So we are in this cavern, at minus 100 meters, we have an object which is as a building of 8 floors sleeping, and if you consider the cross section, is a building of 5 floors. I know
Sonia,
that
does it help? Sorry
yes.
for interrupting. Does it help if I show a slide of it?
Yes, you can show me
exactly,
in the meanwhile. Yes,
one.
exactly. Yeah, because then I will go on the other side. But of course, the perspective here sometimes is not, let's say, easy. What I would like to say is that in terms of sites, CMS is not the largest, the biggest experiment we have at CERN, because we have Atlas, and Atlas is double in length and also let's say 1/3 more in height, because it's 27 meters in the cross section, so a building of 9 floors, and the length is 45, 46 meters, so is double, almost double, I would say. But CMS is twice in weight. Now you see this red part, and maybe if there is the picture, I cannot see, but if there is the picture, you can see also all the red stuff we have here. This red part is iron. How much iron we have here? We have more iron than the amount of iron used to build the Eiffel Tower. And if this can be already impressive, I have how to say, a comparison with the daily life, let's say. Now, a city car. I have an electrical car, a Zoe. It's more or less 1 ton, okay? Now, this object in total has a weight of 14,000 tons. 14,000 tons means an hill made of 14,000 city cars, one on the top of the other, which is, in my opinion, quite surprising. Now, I think we can move a little bit. I don't know if we want to show the side, maybe, and then we go a little bit in the middle. Okay, we can walk with the help of Noemi. What you can see, what I call the fits are the pads, these orange parts. And maybe if we have time on the other side, we can show even yes, with the pins. I don't know if we want to show maybe later. Okay, see the cables. Andromaki, each time you want to give numbers, because I cannot retain all the numbers in my mind, but if each time you want to give numbers or interrupt me, please do.
No problem,
So,
no problem.
Yes, we will.
But yeah,
yeah,
the only thing
sometimes
you have to tell the people is that we have databases telling us where one cable starts and where it finishes, because otherwise it would be practically impossible to track
Yes,
them down.
I think we have tens of thousands of
Yeah.
cables.
Right, you are right. If we have the chance to go to the electronics room going up, you will see that we really need a database and maps. Otherwise, you cannot really understand all the connection. Okay, this is nice because this is one of the, we have many machines here, and they are used to open the detector. Now, again, think of this salami and the cut slides of this salami, because CMS has another peculiarity. It was built on surface. So it was completely assembled on surface, and then it was brought underground. Now, I told you, we have a baby or a beast, you can call it as you want, but however, the total weight is 14,000 tons. And this means that you cannot bring in one shot all the detector underground. So it was built in a very clever way, many slices, and each slice was lowered with the help of a crane underground. This means also that each time you have we have a period of shutdown, let's say. Now we have a long shutdown in this period, but there are also some short shutdown every year. We can open the detector and make operation, manipulation, intervention inside, just because really we open it as an accordion. How do we do this? We use this machine. Now, unfortunately, they have already done many things, so we cannot see here the cables, but there are some cables here, and the job of this cable is to pull the slice in such a way that you can open the detector in the parts you want, and then you can close. Again, I ask again my comparison from Italy as a sort of sandwich. Maybe you can you fill your sandwich and then you put inside. So there are many of these. We will meet also in the other sides. They are doing this job. You can see also many pipes, of course, because we use gas. We have many things, in particular, for example, for the cooling of the magnet, and the cables. As Andromaki said, we need to have really a map of this, otherwise you get lost, okay? And of course, you should monitor with, of course, programs, the signals, and so you can understand from where the problem, if any, is coming from. We are on the other side of the detector. You see? I don't know if it works here. Yeah, it works. So maybe we can, I can show just, you see this wheel. These are the cables I was talking about, which makes us able to, you see these, maybe I can go here. These cables here, you see here, and you see also on the wheel, they are the cables we use to pull the slice of the detector. And this is another part of the machine doing this job. Now I will show you close on the other side. First of all, maybe we can see the beam pipe. Yes, Noemi, and sorry, I can only talk now because I cannot go on the top of the beam pipe, but they installed, okay, this, you can see this pipe wrapped with aluminum, let's say. It's not particularly only aluminum, of course, it's something special. But however, this is, if you want, the LHC. We receive the beam which enters the detector, you see, as a stick. And on the other side, we have the same, and in the center of these 25 meters, you get what we call the bunch crossing, which is to cross. Maybe we have some slides to support this explanation. The bunch crossing is when you have groups of protons smashing together from opposite direction. And then you get the chance that in this bunch crossing, you get some collisions, because we call collision only when you have one proton smashing on another proton. So how to say, another comparison. You want to go to the cinema, there are many people. You want to enter the room of the cinema where there is the movie, and there is the other group of people going out, okay? So at a certain point, you have two bunches of persons crossing each other. And if there are many people, of course, you can get the chance to smash on another, to collide on another person. And this is the collision. While the groups going to one in front of the other, they're called bunch crossing. Maybe we can show here another curious thing. And then I cannot go up to show you the view from the upstairs. I go again to these feet, because again, we are talking about the fact that you can open your detector. As we said, we have this system of cables which are pulling out, okay, the slices of the detector. But okay, this is not enough, because each slice is more or less, let's say, the weight of each slice is more or less 2,000 tons. So it's heavy. What do? We try to, how to say, to make them lighter. So we pump inside these orange pads compressed air. And this means that this compressed air is a little bit, is not, of course, pulling up the detector, but it's is helping to slide it on the floor, okay? And these you can see, maybe Noemi can help me to show part of the system where we send this compressed air here, okay? So it's again, it's a clever idea. And thinking that air can make this job of sliding up and down the detector, make this job easier, is quite, how to say, fancy idea, because it's air. Something we cannot see, we cannot catch, can allow us to make this, this job easier. And then there is another thing I would like to show you. We do not have a magnetic field now here, okay? Fortunately. We can stay here, but the iron I was talking before is still magnetized. So even if now are more or less 1 year and a half, 2 years, there is no magnetic field, let's say, at least in continuous, because some tests that they were done. However, this iron is still magnetized. And I have this expensive, very expensive detector, you see. Please do not laugh, it's an expensive detector, but okay, it's a detector, however, it's not expensive. Now look, with this I can prove to you that this is magnetized. Look, can you see? Okay, and what we can do, Noemi is really challenging me. Let's see if I can do this. And again, this, and again, this. You see? Okay, if there are no physicists, you see, we enjoy with this. This is, for me, is pure, really enjoyment. I can really enjoy with this. And of course, you know what, you can do many things with this. I don't know, we can try to do Another thing I'm used to do, okay, I had to add a few. You see, they are magnetized now. Okay, let's do like that. Let's put another one, maybe, to make it longer. And let's try to do this other thing. You see, this I call the magnetic swing. You see, you can consider that this game you can do even outside. When the magnet is on, we cannot enter this cavern. We can still play this outside. We can still play this outside just because we can feel the magnetic field even outside. Now, why it was going on the floor? Because this means that, okay, this is almost, let's say, the maximum we can have for this, because the weight of this chain is important, enough important that it's fighting with this force, keeping it on the iron here. Okay, I think we can go up if you. Okay, let's go. So we have to. Now we will try to do 5 floors. We will try. Follow me. It's open. Andromaki.
Yes.
In the I don't know. In the meanwhile,
I will. Since you are going up and down, and since you told everybody you gave them the salami model of the detector, I will give them another very intellectual model, which is the rouleau cake of the detector. So the detector does, of course, is made in a way that it can open in slices, but inside the slices, they are not all the same. Because the detector, the way it has been built as a camera that can measure the physical properties of all the coming from all the collisions that happen in its center. So what it has in the middle, it has exactly where the first collisions come. It has something that we call tracker. This is a detector whose role is to show you how the charged particles are generated and how they spread inside the detector. So it's the first part that starts, comes alive when the events occur. So this is the part that gives you information about the charge and about the momentum of the particles that go through it. Then around the tracker, here you see the tracker, you see it's written silicon tracker. In CMS, the tracker is made out of silicon, and it was a major breakthrough having such a large silicon structure at that time. Then after you know exactly how your particles are distributed in space, you want to measure their energy, and you measure their energy in a rather brutal way. You kill them inside specific materials, but they die in a glorious way. They die in light. They produce light, they produce signals that you can record, and by recording the totality of those signals, you know all about the energy of the particles that produce them. Particles interact with matter as far as calorimeters are concerned in a different way, in 2 different ways, electromagnetic and hadronic. There is lots of discussion to be done. But for you to remember is that the electromagnetic interaction happens fast, and it gives you a very nice and easily described distribution of particles. And this is taken care by the innermost part of the calorimeter, which is called electromagnetic. And then you have the ones that interact hadronically, and that's a messy interaction that can take a long way inside the material to happen. And it is really taken care of mostly in the hadronic part of the calorimeter. So when you know the energy, you know the momentum, you know the charge, you know absolutely everything for the particles. But for a very nasty particle whose signature is very important for most physics analysis, which is the muon. The muon is a particle that can travel incredibly long distances with very, very faint interaction with matter. That's why you are being crossed by muons now from outer space, from all sides of Earth, and that's why they are also so very important to our brothers astrophysicists, because they can go for a very long time. So
I confirm.
Yes. So we have somebody. Yes. For us, for high-energy physicists, they are most annoying because they escape. So in order to take them into account, you add detectors outside the length that would contain all other particles. So the calorimeters can eat all the particles of the energies you are putting in, except for the muons. So if you have detectors all around the calorimeters and they see something, well, these are the muons. You have to make sure that these muons come from the center of your interaction, where your beams collide, where your bunches of particles collide together, and not they are random and pirate muons coming from outer space, because then you will make an error. So if you also include the muons inside the picture of your event, you know it all, and the analysis can proceed correctly in identifying whatever they want to identify, because as we said, the CMS as Atlas are multi-purpose detector, and we don't run one type of analysis. It's not Galileo throwing an apple from, it's supposed to be mythology, but anyway, it was not a guy throwing an apple to verify one thing, but it is actually doing lots of research on different topics, taking the same data and looking at it from a different perspective. And this is, of course, how modern physics, also CMS, also astrophysics works. It's several things, several theories that are being tested at the same time. So this is the, yes.
We should say that the poor Galileo, he didn't have any electronics with him, so the poor chap, he couldn't do so fast and so this kind of analysis. Of course.
Possibly we have to say also that that's why he came to such a good conclusion, because he didn't have any electronics.
I think what was this the guy who sang?
Yes.
So he sang as well.
Yes.
So singing is a very good timekeeping.
Singing is very good, also very good. Okay.
May I have one more comment on what you just said about the particle detections? There is one more type of particle that we don't see.
Yes.
Neutrinos who fly through, and so we won't see the supersymmetric particles, the stable ones, and we won't see part of the supersymmetric interactions and the dark matter. But of course, their decay is very significant, so that we would see other parts of their decay. And but this is what we call missing energy and missing momentum. That is also very much important in the physics analysis.
Yes, exactly. So you gave a panorama of those particles. If I can rephrase for let's say the non-expert, because you know that this is something I really like each time to go from the technical point of view through the common daily life. I would say that okay, this particle, they behave as people. For example, Zoltan, you were talking about neutrino. I would say that neutrinos, they are very snob particles, because the basic thing is that in order to understand the nature, the energy, the momentum, as Andromati was saying, of particles, so to reconstruct the identity card of the particles, we need them to interact with matter. And the picture Andromati was describing is exactly showing this, that you have many particles who are very interacting particles as electrons, protons, others you see in the first part, in the central part. And so they stop there because they, how to say, they are absorbed, they die there. The muon is a less interacting particle. This is why it's going, is reaching the edge. And the neutrino we cannot even detect. Now I'm in a crucial point because you see, okay, you see also my finger. I know that Zoltan always complains because I'm unfocusing the system, but this is so nice to show you the beam pipe from here. Okay, you see this stick. This is the beam pipe I tried to show you before. Now I'm in the middle level, and okay, I can only show you maybe a view from the top, but we cannot go because there is a test going on. But maybe from this position, I can show you from the top if Noemi help me the shaft. So the hole from where the detector was lowered. Now you see this, okay, you see this edge and this the other one, okay? So this is the diameter of the hole. And if you go up, you have the surface, okay? And this is from where each slice was lowered in the cavern. And now I would like to show you, if we can move, the distance left between, you see the edge of the detector here, you see, and the wall of the hole. I will go there and I will show you the distance because let's say the diameter of the detector was really was fitting the hole. Now, how did we do this manipulation? We asked a crane from the harbor of Genoa, the typical crane you use for big ships, and this crane was able to lower the detector. Now I go down. Do you want me to keep this? Okay, just a moment. Do we want to just to go? We go down? Okay, yes, we go down. Okay. Because we have also a certain point to close our connection. Let me go here
to
show you.
We still have another 10 minutes, and I would like to encourage the audience to ask questions.
Yes,
Don't hesitate to use the chat of the alumni system. We are watching that. Okay, go ahead.
So you see this? This distance is my hand, you see? So this is the distance. This is the wall of the hole, and this is, let's say, the cage, okay, the structure of the slice. This was the space left between the wall and the slice, okay? And this, what does it mean? That when you have a very big object, let's say if I can do this, I don't know. No, I cannot do this. It's really complicated. However, I will do this. If you have a big object, you have to go inside, okay? You have to avoid for sure any oscillation, okay? Otherwise, just to remind ourselves, Galileo, you start to have a pendulum, okay? And so you completely destroy your detector. So the operation to lower the slices inside the cavern took in average 8 hours for the lightest slice, for the central part of the detector, which contains the magnet, and so it's even heavier. It took 12 hours. So now, if there is somebody who wants to play with numbers, just calculate with a constant velocity. You know, 12 hours, you know, more or less 100 meters, you can calculate the velocity, but I will not do now. Okay, you were asking something, Zoltan? Okay,
yes.
There are I don't know, there are questions? Or
not yet, not yet. Majana is watching that. We not yet seeing any questions, but fortunately we have people around who are watching our broadcast.
Yes.
Yes, I really encourage, because how to say, you can have many curiosity, because of course I'm just showing you what we have here. But for example, imagine people who is working inside here. Sometimes now we have the detector which is completely closed, but when it's open, you can see people here inside the hole, and I can tell you that one person fits more or less the distance from the basis to the beam pipe. And so they are really has ants, you know, working all inside because, okay, this is a building of 5 floors. I would like also to say something else, that this big structure, each piece, now we cannot show you inside, but maybe again, Andromaki, maybe she can show with the slides. She said that yes, we have many layers inside.
Yeah,
each layer, yes, exactly. Each layer, you see each color, the blue, the yellow, the white, okay, which is the magnet, and also then the red on the edge and the gray on the edge. They should be connected with not only with cables, but also from the mechanical point of view, they should follow an alignment, as we say. So in the alignment, the correspondence in, let's say, in a mechanical correspondence between one layer and the next one or the previous one is at the level of microns. Now, microns is less than a human hair, okay? It's 1 million times a meter. So this is a really challenging thing because you have to take under control with a very high precision an object which is huge. It's a building of 5 floors, guys. It's really huge. Even if it's not the biggest one, it's really huge. And then, okay, to be correct, to keep this alignment, maybe we can show also this thing. Now, we don't have the detector here. We have on the other side, we can go, which is, this is not only a job for physicists, and not only applied physicists, but also for engineers. You see this one. Okay, we have to check that the cavern is not moving, because if you move the floor, of course you move also the detector. And this means that you could lose the alignment among these layers, or in any case, you have to take into account when you have your analysis, you have to take into account if there was any shift or any changes between these layers. Otherwise, what is coming from the center of the detector is going out to the edge, cannot be connected, okay? So we really need civil engineers, physicists, electronic engineers, very good technicians helping us for all this. Who I don't know if
mechanical engineers,
yes,
cooling.
Mechanical engineers,
cooling,
yes,
gases.
cooling, yes, exactly. So
gases.
This, yes, is really a team of many kind of roles collaborating for a unique goal, which is to find the results. Now, maybe Andromaki, we should say why we are interested in these results, because we are physicists. I don't know. What do you think about?
No, I think it's always, I mean, it's a very, our language is mathematics. So let's be frank about it. After all that, all the physics research has to be explained in terms of elaborate mathematical formulas and using any, but elaborate but universal. So everybody can understand everybody. So however, so the mathematical models are modeling of possible ways that the universe has been evolving, and the way the world as we know it is made is all physics. And in that sense, all human beings are physicists because we all think about it all the time. However,
I agree completely
we
what
are
you
all
are
physicists.
saying.
However, physicists, we are all potential physicists. However, the real physicists are the ones that can put these thoughts into a way of, into calculations, can check several probabilities and can refuse several hypotheses and continue building. We always, in science, we stand on the shoulders of giants because we always take from what people before us took a lot of pain in building, and lots of theories have come, have been thrown out, and we continue. It's the story of humanity, I think. But then, I mean, all this is very nice that I tell you, we think about this, we love that. However, doesn't make any politician give a cent for that, because here we need money, we need research, we need education, we need outreach, we need several things. All these things that you see behind you is a lot of technology, a lot of development, a lot of R&D, a lot of startups. A very tiny fraction of this will come to our lives passing through industry. CERN is an organization that creates lots of such things, and then they can freely go to industry under certain conditions. So it's lots and lots of technology, and technology and science go hand in hand, because several of the things that we are able now to do, the building of LHC, the magnets, the future accelerators, depend on technological progress that will take place before, so it can be used. As I told you, the silicon strip, the silicon detector was a dream when myself and afterwards Sonia came to CERN, and we worked at the lab detectors, because there was simply not enough technology in order to produce it. And then 15 years after, you were able to produce it just because of the technological progress. So we go in science hand in hand. Yes.
No, it's just to support what you are saying. It's not only in this word, because I really like to stress that you are talking about the silicon detectors. Now, when we go, for example, in the hospitals, and I don't know, for example, we are using some medical investigation as can be, okay, let's start with the magnetic field and with factories, and then so this know-how and technology transfer going outside. But there is also an impact on our daily life. And maybe if all physicists, they are looking to understand how the universe was born, etc., evolving, etc. And so it's me, Andromaki, and all the physicists at CERN. Of course, even if people who is not really interested in fundamental physics can always gain something from this research. This is really worthwhile, at least to know a little bit about these words, because okay, sometimes you have to wait. Something which we are studying today maybe will be useful in 40 years, so maybe it will be useful in 2 years. Electronics is an example as how fast we can, how to say, upgrade our mobile phones with new and faster electronics or whatever. And the computers is the same. If you think 20 years ago, okay, let's say computers, we had computers, but completely different computers as we are now. So this is really a world where you start, it's a sort of startup of knowledge, I would say. And let me say also another thing that I really agree with Andromaki. All of us, we are physicists. Then you have technicians of physics, which are the real physicists doing this job. But each of us is, Andromaki can correct me, that physis in Greek means nature. Is it?
Yes,
yeah.
It's nature.
So we are simply
you are part of nature, you are in it. No way not to escape.
So now, everybody is part of nature. And so this is why anybody is a little bit physicist, maybe technical physics or simply passionate of physics. And this is at least my point of view.
Sonia, thank you very much. I think this was a very nice sentence, ending sentence. I would like to thank for everyone.
Yes.
For the visit today.
We go out in the meanwhile, Sultan.
Yes.
Yes, exactly. And I think this could be a very nice closing picture.
Yes, absolutely. Absolutely. So remember that you are part of physics, so you are physicists. It's nature. Nature is
Yes.
here, but also it's something very modern, CERN, because it produces lots of technology, and something else, it produces the human interactions in between the largest international community of young people, and this is the real strength of CERN. The real strength of CERN is the people that collaborate with CERN, who are young and enthusiastic most of the time. Okay, that's
Thank you
the
very
real
much.
force.
Thank you very much, Maki. And thanks for joining us today. And we wish you a very pleasant alumni day continuation. Thank you very much and see you soon in the future.
Bye.
Thanks. Bye.
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 Bye. Bye. Bye.
Bye.
CMS.